Let's take a look at this scalar or dot product, which involves an operation between two vectors. The scalar or dot product in the geometric system is defined in terms of the length of the two vectors and the angle between the two vectors. So consider the vector A and B in 2D, then we could take the angle between those two vectors and take the cosine of that angle, and we're halfway there in terms of the dot product. So the dot product is equal to the length of A times the length of B times the cosine theta. This function is commutative because if you just switch the order of A and B, that's all you're doing if you switch the order of A dot B. So the commutative law is obeyed. The dot product is distributive, meaning that if you form the sum of two vectors and then dot it into A, that's the same thing as dotting A into B plus A dot C. These are easy to prove. So here we have again the 2D representation, and the first thing we want to realize is that holds in 3D also. You just have to find a way to determine the angle between the two vectors. So let's go back to 2D. If we look at the projection of A onto B, that projection will be the length of A times the cosine of theta. This is equal to the projection of A onto B. So the dot product is equal to the length of B times the length of the projection of A onto B. Realize that this is a scalar, and so is this. The dot product is a scalar quantity, and that's a very important thing to remember. So if A is perpendicular to B, so if A were just simply to be along this axis, then our cosine theta would be the cosine of 90, which is 0. When you have two vectors that are perpendicular to each other, the dot product is equal to 0. The maximum value of A dot B is when A and B are parallel. Normally you would consider the case first that theta is equal to 0, which means that A is lying in the same direction as B. But you could also consider 180, so if A heads off in this direction, then you have theta equal to 180. So if you remember, the cosine of 180 is -1 and the cosine of 0 is 1, so that's why you get a maximum length for those two cases. So we have to take into account this minus sign for the 180 case. Cosine theta is equal to plus minus 1. A dot B is equal to plus minus the absolute values of the vectors, which means their length, and we usually write that as just AB. If A equals B, then you have A dot A is equal to A times the projection of A onto itself. If you multiply those together, you just get the length squared. If you take the dot product of A with itself, you're getting the length of A by just taking the square root. The length of A is equal to the square root of A dot A. And of course all of these are scalars because the dot product is a scalar. While there's lots of applications, the ones that relate to what I've already said is that you can determine the component of a vector parallel to the B, and so you'd end up with A dot B being the value of the dot product because cosine theta is equal to 1. And then we've already talked about anti-parallel. If A is equal to minus B, or at least in that direction, then you would have the dot product just being minus the length times the length. And if you have perpendicular vectors, you'll end up with 0. Another application is just to find the cosine of the angle between two vectors. If you look at the definition of A dot B, you can solve for cosine theta, and so you'd have the length A times the length of B times the dot products. And so that'll give you the cosine of theta, from which you can get the angle theta. Here's some other examples. The potential energy of dipoles in fields is dependent upon the orientation. If you have an electric dipole, which we would call P, vector P, in an electric field, which is a vector E, then it turns out that the potential energy of P in the E field is going to be equal to minus the dot product. The electrical potential energy of this system depends on the angle between these two vectors. The magnetic dipole moment, m, in a magnetic field B has a magnetic potential energy, which is m dot B with a minus sign. If you look at these vectors here, and let's just take the case of the electric dipole. So if you have this P here, this is the electric dipole moment, at an angle theta with the E field, then you might ask, well, what angle will give you the maximum potential energy, and which angle will give you a minimum? At theta equals 0, the electric potential energy is minus PE. When you have P opposite to E, you have the highest potential energy, which is plus PE. This is the lowest energy state, so if you were to take this vector and just rotate it 180 degrees, then what you have then is a unstable equilibrium if it were actually anti-parallel to E. As soon as you deviate that by any small amount, the electric field will want to cause this to flip. And that's what we mean by having maximum potential energy here, wanting it to go in parallel to the E field. So here it is again. This is the maximum value, this is the minimum value, and the dot product is giving you that result just from this equation right here. So let's take a look at the example of finding the projection of A onto B in a vector form. So we want to find the vector which is equal to the magnitude of the projection of A onto B in the direction of B. So we want to write P of A onto B in terms of dot products. As I said, the direction of the projection will be parallel to B. What is P? Well, it's the magnitude of this projection, so it's the absolute value of P, times the unit vector in the direction of B. But what is that? Well, it's the vector B divided by the magnitude of B. That gives us a unit vector in the direction of B. If we know that the projection of A onto B is equal to the length of A times the cosine theta, and remember that's a scalar, then the projection of A onto B, the magnitude of that, we can get from the dot product. So here we go. Here's the dot product, here's the length of B, and the projection of A onto B. And that gives us a scalar quantity which is equal to A dot B. So let's look at this then. Here's our A dot B, which is equal to the length of B times the projection of A onto B, and so that's defining the projection. If we divide that by B, then what we're doing is taking the scalar product, dividing it by this quantity here, which is giving us this quantity right here. The dot product divided by B is going to be then the length of the vector P. So then we multiply by this quantity here, which is the vector B hat, so all of this is B hat. And so we have this last factor. This last factor is a unit vector in the direction of capital B. So putting that all together then, the projection of P vector is equal to A dot B divided by B dot B times B. So I've just replaced the magnitude of B and B so that we get this quantity here. So this is a scalar right here. Two dot products give you scalars, times a vector, so we end up with a vector. If U is a unit vector along the direction, say a coordinate axis, doesn't have to be, so U is a unit vector along some direction, and so if we have a coordinate axis, let's take the x-axis, then P dot U is the component of P in the direction of the U vector. So this is in the direction of the unit vector U. And so for a coordinate axis like the x-axis, this would be P sub x. One question that you can very simply work out, suppose you have the unit vectors in the Cartesian coordinate system, so you have I, j, and k. The question is, find all combinations of I, j, k and determine their dot products. So this is something you can work out very, very quickly. Consider the inverses. So I dot j, j dot I. Think of all the possibilities and determine the dot products. Now let's look in terms of components. we go back to letting A be written as a set of components with the unit vectors along the axes, the coordinate axes, and here's B, this similar expression. We want to write this in terms of the components, the dot products. By the way, when you put the dot at the bottom instead of the middle, it's a lot easier to write many times if you're using a computer. That turns out to be the Mathematica form of the dot product. We know that the dot product commutes, so if we take the dot product, which is equal to this vector dotted into here, we can move the dot between the various components so that it looks as follows. We can write this component dotted into the vector B plus this component into the vector B, and then this component into the vector B. Now remember that all of these unit vectors are perpendicular, so for example x hat dot y hat is equal to 0, which you would have determined if you did the previous question. Each unit vector has unit length and is parallel to itself. So for example, x hat dot x hat is equal to 1. So if you take all of the terms, so for example ax, bx, x hat dot x hat, then you can simplify it, and the only survivors on the right hand side is this series of products ax, bx, ay, by, and so on. So therefore the dot product is equal to this quantity here. And so this is the way in the Cartesian coordinates you determine the dot product. We often use a notation which is called Einstein Notation, that if you represent the x, y, z's as 1, 2, 3, then you can write this expression here as a sum over I. So you'd have a1, b1 plus a2, b2 plus a3, b3. And that's what it means to change the index here. Given that notation, that the idea is that if you have two repeated indices, you can write that as this simple relation here, which means to sum the products. This is the summation of the products. But if you have this repeated index, then you sum over the dimension of the space. For 3 dimensions, this is 3, and you could have done it in 2 dimensions, then therefore it would only be a 2. We use this summation rule all the time. Einstein once said that it was one of his best inventions in his lifetime. There's some obvious results that you can write A as a sum over A sub I, E sub I, where this is the unit vector in the ith direction. So for example, if you say E2 like that, then what you're saying is that's equal to y hat and that's equal to j hat. If we have the repeated index, then that means to sum over I, and that'll give you all 3 components of the vector A. So we have a vector here, and we have vectors here, and so we end up with a vector. If you take the vector A and dot it into the unit vector that corresponds to I, that'll give you A sub I. Realize this is not a sum, this is the projection of A onto the ith axis, and that's what we call A sub I. So if you wanted to, you could draw this out. Look at a vector A, take a unit vector, say in this direction. The x component, or this component of A, is equal to the dot product of A times the unit vector. Another statement is that if A dot B equals 0, and A is not equal to 0, and B is not equal to 0, then A is perpendicular to B. If the dot product is equal to 0, and these are non-zero vectors, then the 2 vectors are perpendicular to each other. So next time we'll talk about vector cross products. So this is the other type of multiplication that we use in vectors, and all of this is just vector algebra.